Hello! In this video, we are going to prove the following theorem. If delta is a gauge defined on the closed interval a comma b, then there exists a delta-fine partition of a comma b. Now first, let's talk about partitions. So let's consider the closed interval a comma b. Well then, a partition of a comma b is a collection of non-overlapping closed intervals whose union is the closed interval a comma b. So something like this. This collection of closed intervals would be an example of a partition of the closed interval a comma b. And we could label them I1, I2, I3, and so on. And we may also label the endpoints of these intervals x0, x1, x2, and so on. So in that case, for each interval I, this is just the interval xi minus 1, comma xi. So that's essentially what a partition is. A tagged partition is when we select a point from each of these subintervals. And let's say the points that we select are these. And I'll label these points T1, T2, and so on. These points that we select are often called tags. So in some cases, a partition is just the collection of intervals. So in this case, I1, I2, and so on up to I5. But the tagged partition, which we usually label with a dot on top, is the collection of intervals along with the tag in that interval. So now, let's talk about what a gauge is. A gauge on the closed interval a comma b is a strictly positive function defined on a comma b. So for example, if we consider the function delta of x equals x squared plus 1, where x can be any element of a comma b, well then this would be a gauge on a comma b, because we can take any element of a comma b, send it into the function, and the output value is always positive. Right, so that's all a gauge is. So now, our definition of a delta-fine partition is as follows. Given that delta is a gauge on a comma b, and p is a tagged partition of a comma b, we say that p is delta fine if each subinterval ii is a subset of this interval, which is centered at the tag ti. So the way you can visualize this is if we consider the subinterval ii of our partition, we'll say it looks something like this. And ti is the tag of the subinterval ii. We'll say that the tag is right here. Well then, this interval is an interval centered at ti, and ii is contained in this interval. So we'll say that this interval centered at ti is like this. So the endpoints of this interval are ti minus delta of ti and ti plus delta of ti, right? The radius of this interval is really just the output value of when we send the tag ti into the gauge. So essentially, for a partition to be delta fine means that this needs to happen for each subinterval of the partition. So we need I1 to be a subset of this interval centered at T1. We need I2 to be a subset of this interval centered at T2. We need I3 to be a subset of this interval centered at T3. We need I4 to be a subset of this interval centered at T4. And we need I5 to be a subset of this interval centered at T5, right? That's what it means for a partition to be delta fine. Okay, so now let's get into proving this theorem. To start with the proof, we consider the following set. We consider the set E, which is the set of all elements x in the interval a comma b, which is open at a and closed at b, with the property that there exists a delta-fine partition of the closed interval a comma x. Now the reason why we have this interval open at a is because if you imagine an element x in this interval, well then no matter what x is, x will always be strictly greater than a. So if we want to imagine a partition of the interval a comma x, well, it makes sense because a is strictly less than x, right? So it's always a non-trivial interval. So you can imagine partitioning it, right? But it doesn't really matter. In any case, we're going to show that E is non-empty and bounded above. So then by the completeness property of the real numbers, that implies E has a least upper bound. So to show that E is non-empty, we consider the following value. We consider the value m, which is the minimum of a plus delta of a and b. Now, since m is the minimum of these two values, that means m is less than or equal to both of these values. So in particular, we know that m is less than or equal to b. But also, we know that m is equal to one of these values, and both of these values are strictly bigger than a. So m must be bigger than a. And this tells us that m is an element of this interval. So m satisfies this condition. So now we want to show that there exists a delta-fine partition of a comma n. But the claim is that the interval a comma m itself, along with the tag a, is a delta-fine partition of a comma m. And to verify that this partition is delta-fine, all we have to do is verify that the interval a comma m is a subset of that interval centered at a, which is a minus delta of a comma a plus delta of a. But we can see that this happens because we know that a minus delta of a is less than a, and a is less than m, and we know m is less than or equal to a plus delta of a, because m is the minimum of these two values. So these inequalities imply that this set is a subset of this set. So that shows that this is a delta-fine partition of a comma m. And that shows m is an element of E. And hence, E is non-empty. But also, we know that E is bounded above, because every element of E is less than or equal to B. So E is bounded above by B. So, since E is non-empty and bounded above, then by the completeness property of the real numbers, that implies E has a least upper bound. And we're going to let U be the least upper bound of E. Now, since U is an upper bound of E, this means U is greater than or equal to every element of E, which are all greater than A. So U is greater than A. But also, since U is the least upper bound of E, and B is an upper bound of E, then U must be less than or equal to B. So this shows that U is an element of this interval. So U satisfies this property. And the claim is that we can show U is an element of E. So we can show that there exists a delta-fine partition of A comma U. And to do that, well, first, since U is the least upper bound of E, this means anything smaller than U is not an upper bound of E. So in particular, U minus delta of U is not an upper bound of E. And because of that, well, this means U minus delta of U is not greater than or equal to every element of E. Instead, U minus delta of U must be strictly less than some element of E, and I'll call that element V. And since U is an upper bound of E, we know that U is greater than or equal to every element of E. So in particular, U is greater than or equal to V. So we have this. So there's two possibilities. Either V is equal to U or V is less than U. Now if V is equal to U, then we're done. Because V is an element of E would imply U is an element of V, since they're both equal. So that covers the case V is equal to U. So now we're going to assume V is strictly less than U. Well then, since V is an element of E, well by definition of the set E, this means that there exists a delta-fine partition of the interval A comma V. And I'll call that partition P. So we have a delta-fine partition of the closed interval A comma V. But the claim is we can also find a delta-fine partition of the closed interval V comma U. And in fact, that partition is going to be the interval V comma U itself with the tag at U. And to show that this partition is delta-fine, all we got to do is show that the interval V comma U is a subset of that interval centered at U. And that interval was U minus delta of U, comma U plus delta of U. But we can see that this happens because we have U minus delta of U is less than V, is less than U, which is less than U plus delta of U. Right? These inequalities imply that this inclusion holds. So that shows that this partition is delta-fine. So because we have a delta-fine partition of the closed interval A comma V, and we have a delta-fine partition of the closed interval V comma U, well then if we glue those partitions together, then their union will be a delta-fine partition of the closed interval A comma U. And so we have found a delta-fine partition of the closed interval A comma U, which means we have that U is an element of E. So we've shown that U is an element of E, but the claim is that U is equal to B. If we can show that, then that tells us B is an element of E. And so there exists a delta-fine partition of A comma B. And so that will complete the proof. To prove that U is equal to B, well, we know that U is less than or equal to B. So to show U is equal to B, let's assume for a contradiction we have U is less than B. So what goes wrong if U is less than B? Well, the idea is, right, let's think about our interval. U is less than B in this case, so let's just say U is right there. Well then, let's consider the quantity U plus delta of U, which is bigger than U, right? But it might be bigger than B, we're not sure. But certainly, no matter how big U plus delta of U is, or no matter how small it is, we can always find an element between U and U plus delta of U, we'll call it W, and W also lies between A and B. And the claim is that this element W will belong to E. If we can show W is an element of E, that means we have an element of E that is bigger than U. But that contradicts the fact that U is an upper bound of E. So to show that W is an element of E, we want to show that there exists a delta-fine partition of the closed interval A comma W. And to do that, well, let's first note, since U is an element of E, we know that there exists a delta-fine partition of A comma U. And I'll call that partition Q. So we have a delta-fine partition of A comma U, But the claim is we can also find a delta-fine partition of u comma w. In fact, the delta-fine partition of u comma w is just going to be u comma w itself with the tag at u. And how do we verify that this is a delta-fine partition of u comma w? All we got to do is show that u comma w is a subset of that interval centered at u. Right? And that interval is u minus delta of u, comma, u plus delta of u. Right? But we can see that this is true because we have that u minus delta of u is less than u, which is less than w, which is less than u plus delta of u. Right? So these inequalities imply that this inclusion is true. So this must be a delta-fine partition of u comma w. So because we have a delta-fine partition of a comma u, and we have a delta-fine partition of u comma w, well then their union must be a delta-fine partition of the closed interval a comma w. And so we have found a delta-fine partition of a comma w, and that shows w is an element of E. But w is greater than u, so that contradicts the fact that u is an upper bound of E. Our assumption that u is less than b led us to a contradiction. And remember, we know that u is less than or equal to b, but since we've just shown that u cannot be less than b, we must have u is equal to b. So since u is equal to b, and u is an element of E, that tells us b is an element of E. And so, since b is an element of E, that means there exists a delta-fine partition of a comma b. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.